In this section, we'll be looking at what determines the relative strength of an acid or base. So we know that the behavior of an acid when it's dissolved in water can be described by its Ka. We call this the acid dissociation constant, or sometimes it's called the ionization constant for an acid. They're the same thing. And when an acid is dissolved in water, it donates a proton to the water, which functions as the base. This forms the hydronium ion and an anion. Ka, the acid dissociation constant, is just simply products over reactants. And remember, we don't have to include the water as a reactant because it is a pure liquid. And all we have to really keep in mind is that weak acids have small Kas, much less than 1, and strong acids are going to have big Kas, much greater than 1. Tables of these are in the back of your book, should you need them. When a base is dissolved in water, we can describe what's occurring via the Kb reaction. And so in this case, what's happening is the water functions as an acid, transfers a proton to our base, produces the conjugate acid of our base, which will be a cation, and the hydroxide anion. So Kb, the base dissociation constant, or sometimes it's called the base ionization constant, is simply it's our products over our reactants. And again, we don't include the pure liquid water in our reactant as a reactant. Now, weak bases have Kbs that are a lot less than 1, and strong bases have Kbs that are a lot greater than 1. Strong bases tend to be metal hydroxides, generally only those from group 1A, and some of those from group 2A are soluble, and weak bases tend to be nitrogen-containing compounds, a class of compounds called amines, and perhaps the most famous one, ammonia. Okay, so one of the things that we do know is that increasing the number of oxygen atoms attached to the central atom of an oxo acid increases the strength of the acid. And we know that once we get to 2 or more oxygens and hydrogens, then our acid becomes strong. So here's sulfuric acid, H2SO4. It's a strong acid. And what happens when it functions as an acid is it loses these protons, and the electrons that were in the bond, and they become 100% associated with the oxygen atom. So this gives rise to 2 protons getting transferred, and then we have this doubly negative charge, but it's kind of spread over the whole thing because there's going to be multiple resonance structures where these double bonds are in different positions. And you'll remember from our discussion of formal charge in chemistry 162 that there are 2 double bonds in the sulfate anion. So this is often described as what we call resonance stabilization. The double negative charge ends up dispersed across the entire anion. If we look at something like H2SO3, which is a weak acid, because it just has 1 more oxygen than hydrogen, then what we see is when these hydrogens are transferred, we form 2H+, the electrons that are associated with this oxygen-hydrogen bond become, those electrons end up becoming 100% associated with the oxygen. And you can see that now we have a double negative charge again, but there are fewer resonance structures that we can draw. There are less ways of dispersing that charge over the anion that is formed, and so it is not as stable, and as a result, H2SO3 is weak and favors the left-hand side, whereas H2SO4, where it can really stabilize and disperse that negative charge on the anion formed, that's a strong acid, and it's really not in equilibrium at all. So more oxygen atoms leads to more ways of dispersing the charge on the anion that is formed, and as a result, that anion becomes more stable. So the question becomes now is, does the nature of the central atom in the middle of the oxo anion have any effect on the acidity of the compound? So we're going to look at a series here of oxo acids that all have chlorine as the central atom. And they illustrate this idea nicely about how the negative charge that is formed on the anion stabilizes and increases the strength of the acid. So HClO, we only have one oxygen atom. And so, can only, when this guy ionizes, you can only disperse that negative charge over 2 atoms, right? And so Ka is really, really, really small. HClO2, we've stepped it up to 2 oxygen atoms now, and when that proton is lost, that negative charge can end up being dispersed across 3 atoms, and as a result, it's like 1,000,000 times bigger Ka. So it makes a huge effect. When we go to HClO3, well, now we know that we have 2 more oxygens than hydrogens, so we're expecting this guy to be strong. And when the proton gets transferred, you can see that the negative charge that is formed can be dispersed over 4 atoms, and that makes this guy actually a strong acid. When we get to perchloric acid, where we have 4 oxygens, 3 more oxygens than hydrogens, when that proton is lost, that the negative charge is dispersed over 5 atoms, and this is a very strong acid. We wouldn't even in any way be considering the reverse reaction at all. It just goes 100% in the forward direction. And perchloric acid is a well-known strong acid. Alright, so our rule of thumb for judging the strength of oxoacids is this: if the number of oxygen atoms is more than 2, or 2 or more, I should say, 2 or more rather than more than 2, 2 or more, than the number of hydrogen atoms, then the acid is a strong acid. So a good example here, we've got 2 more oxygens than a hydrogen, so that's strong. We've got 3 more oxygens than a hydrogen, so that's strong. We've got 2 more here, so that guy is strong. Now, if the number of oxygen atoms is, and I should say less than 2, then the number of hydrogen atoms, then it's going to be weak. Okay, so good examples here, we've only got 1 more oxygen than hydrogen, so it's weak. Here we've only got 1 more oxygen than hydrogen, so it's weak. And here we've only got the 1 more. Okay, so that's our rule of thumb. So like I said, now though, we want to talk about what's the effect on that central atom. Alright, so the strength of oxoacids is also related to the identity of the central atom. So here are a bunch of acids where they all have the same number of oxygen atoms, but the central atom is varying. And it's all about that electronegativity of the central atom. And what we see is as the electronegativity of the central atom increases, the acid strength as characterized by the Ka also increases. So this guy's got a pretty big Ka, 10 to the minus 8. This one, it's like 10-fold smaller, 10 to the minus 9. And this one here is 1,000 times smaller, 10 to the minus 11. So what's happening? Well, the central atom is pulling electrons towards itself because it's electronegativity. And the more that it does that, the more that bond to the hydrogen is weakened, and the better the acid that compound is. So if you want to look at, that's what we want to consider when we're looking at the identity of the central atom and how it affects the strength of an oxo acid. All right, so classic questions for this would be like ranking questions. So it says select the correct order of acid strengths, and these are all going greater than, greater than, greater than. So we're going to be going from strongest to weakest. So anything that doesn't have the strongest acid in the first spot is incorrect. So I like to label them. This is a weak acid. This is a weak acid. This is a weak acid. This is a strong acid. And how I'm doing that is by looking at the number of oxygen atoms. Oxygens are equal to hydrogen. Oxygen is equal to hydrogen. Oxygen is 1 more than hydrogen, so it's still weak. Oxygen is 2 more than hydrogen, so it's strong. Now this is totally incorrect because you can't have the strong acid last. Let's do it again. Strong acid, weak acid, weak acid, weak acid. And I'm doing that again by looking at the number of oxygen atoms. So that one is no good because it's got the strongest acid last. Okay, let's go to D, and you can see why I didn't choose D. This is a weak acid, strong acid, weak acid, weak acid. So it can't be D either. But if I go to C, strong acid, weak acid, weak acid, weak acid. So at least it's got the possibility, and if I was hurrying, then I'd just stop there. But the next thing is HClO2 really a stronger acid than HClO? And it is, because it has more oxygen atoms, so that looks good. And then I have to ask myself, is HCl really greater than HBRO? And HClO greater than HBRO? And it is, because electronegativity decreases, right, as we go down, so it decreases. So that means that chlorine is more electronegative than bromine, so we would expect HClO to be a stronger acid than HBRO. So that is most definitely correct. Now, there are some cool things that we can do. If we're given the pH, which is really the same as giving us the equilibrium hydronium ion concentration, which we'll frequently just write as H plus equilibrium, and the initial concentration of a weak acid, you can calculate your Ka. Okay, so I'm going to go through this example now. It says, I have a 0.1 mole per liter solution of the weak acid HA, and it has a pH of 4. So this would be something very, very simple to prepare. I could use a volumetric flask to create this solution, and then I could use a pH probe or a pH strip to measure the pH of it. So what does it all mean? Well, here's the acid dissociation reaction. HA is in equilibrium with H plus and A minus. And initially I have 0.1 mole per liter of my weak acid. I have no hydrogen ions, and I have none of my conjugate base of my acid. So what way is it going to go? Well, it has to go towards the zeros. So it's the acid concentration will go down by X, my hydrogen ion concentration will go up by X, and my anion concentration, my conjugate base concentration, will also go up by X. So what does that leave me? It leaves me that my equilibrium concentration of my acid is 0.1 minus X, and my equilibrium concentration of my products are each X. Now here's the thing though, I've been told that my pH is 4. So what that means is that the negative log of my equilibrium hydrogen ion concentration is equal to 4, right? So what do I know is that 10 to the negative pH will give me my equilibrium hydronium ion concentration, or my equilibrium H plus concentration. So I can solve for X, right? X is just going to be 10 to the negative of my pH, or 10 to the minus 4. So once I get that, I can go ahead and solve for what Ka is, right? So Ka is just going to be X by X on 0.1 minus X, and X is 10 to the minus 4. Okay, so now I've got everything I need to solve for my Ka, and all I had to do was prepare the solution and then just measure the pH at the end. So that was pretty simple. So there are other ways other than Ka of expressing the extent of dissociation of an acid, and a very common one is what's referred to as the percent ionization, or sometimes it's called the degree of ionization. And all it is that when we have a weak acid, if we take the ratio of the equilibrium hydrogen ion concentration to the initial acid concentration and times it by 100. That'll give us the percent ionization. Now, there is a little bit of difficulty with this, is that it does depend on the initial acid concentration. So it is for a solution with a particular initial concentration. So it isn't a constant like the value of Ka is, but arguably it's a little easier to interpret, especially for a lay person. So here's a problem about formic acid, that stuff that I said that is found in ant bites. And it says we've got a 1 mole per liter solution of formic acid, and we measure it and we found that it has a pH of 1.88. What is the percent ionization? So here's my ice table. I started with 1 mole per liter formic acid, and I have no hydrogen ions and none of the conjugate base, the formate anion. It's going to always move towards the zeros, so this will go down by X, this will go up by X, this will go up by X, leaving me with equilibrium amount of formic acid of 1 minus X, and then each of my products will have a concentration of X. Okay, so what do I know? I know that X, my hydrogen ion concentration, will just simply be 10 to the minus pH. So X equals 10 to the minus 1.88. And when I do the math on that, I get that, right? So now I go ahead and I calculate my percent ionization. My equilibrium concentration of H plus is just my X, 10 to the minus 1.88 or 0.0132. And then my initial concentration of my acid, well, that was given to me, it's just 1. And then I got to times that by 100. So this acid, a 1 mole per liter solution of formic acid, only 1.32% of the molecules ionize, right? So that's why it's a weak acid. Remember, if it was a strong acid, the percent ionization would be 100%. Okay, so I'm going to illustrate now that we have to be a little bit careful with the percent ionization, because it's, as I said, dependent on our initial acid concentration. So what we're going to do now is we're going to go through and we're going to show what the percent ionization is for a 0.1 mole per liter solution of formic acid. So when we had a 1 mole per liter solution of formic acid, what happened? Well, we begin 1 mole per liter formic acid, and we have no H plus and no formate anion. It dissociates. It's going to go towards the zeros. It can't go the other way. This will go down by X, this will go up by X, and this will go up by X. That gives me 1 minus X of my acid, and then X moles per liter of each of my products. We know that X is equal to 10 to the minus pH, and the pH was 1.88, and so that gives us our value for X. What I'm going to do now is I'm going to use that information to calculate Ka. So here we go, Ka, it's just our product ion concentrations divided by our reactant concentrations. So I've done all of that and I've got Ka. Now the cool thing about Ka is, unlike the percent ionization, it's a constant. So I can use this to solve for my 0.1 mole per liter solution, right? Because this is a constant. So now what I can do is I can create an ice table for my 0.1 mole per liter solution. So here I've got formic acid in equilibrium with hydrogen ions and the formate anion, its conjugate base. But now my initial concentration of formic acid is 0.1 mole per liter. Right at the beginning, these are going to be 0 and 0. And then it's going to move to the right to come into equilibrium. It's got to go to the right because these guys are 0. So this is going to go down by X. And then these two each will increase by X because the stoichiometry is all 1 to 1 to 1. So at equilibrium, I will have 0.1 minus X of my formic acid and then X moles per liter of each of my two products. So I can write the equilibrium constant expression for this, Ka, because it's a weak acid, so it's going to be my product ion concentrations multiplied together, divided by my undissociated acid concentration, my reactant. So this is just going to be X times by X divided by 0.1 minus X. I'm just getting these numbers straight from my ice table. And we know from our previous work that that is equal to 1.77 by 10 to the minus 4. Now we got this from working with the 1 mole per liter solution, but remember equilibrium constants are exactly that, they're constant. So then I used my solver and I got my value for X. That was pretty easy. I just put this formula into the solver and then I actually set the conditions, and so the concentration for X, it has to be somewhere between 0 and 0.1. And that made it really easy. It just popped out the answer. There it is for X. And then I just put that into my percent ionization formula, which is the equilibrium concentration of H plus divided by my initial concentration of my acid times by 100. And so sure enough, 4.12% ionized, which is good. We would expect that because our formic acid is a weak acid. So it's got to be less than 100. But here's the thing that's really interesting. The percent ionization is not a constant, right? For our 0.1 mole per liter solution, it was 4.12 ionized, but for our 1 mole per liter solution, it was 1.32% ionized. So it depends on the concentration, and it's kind of like, this is perhaps arguably more intuitive for a beginner to understand, the idea of percent ionization, but it's less useful for an expert because it is not a constant. That's why we like Kas to tell us how strong or weak acids are. Okay, when a weak base, and the classic one is ammonia, is dissolved in water, it accepts a proton from water. That's what it means to be a base, is that you're a proton acceptor. And this forms the ammonium cation, the conjugate acid of the weak base ammonia, and the hydroxide anion. And we've mentioned this earlier, when we dissolve a weak base, we can characterize its equilibrium by Kb. So again, it's our product ion concentration divided by our reactant concentration. We don't have to include the water here because it's a pure liquid. And I talked about this earlier. That has a value of 1.76 by 10 to the minus 5. So we can do similar types of calculations for Kb ice tables as what we saw for formic acid. The thing to keep in mind here is that we'll often be talking about pH, but what we really will be needing is hydroxide ion concentration, and we're going to take advantage of this relationship that pH plus pOH always gives us pKw, which is 14 at room temperature. So here's a great example. It says, what is the pH of a 4.5 mole per liter solution of ammonia? And then it gives you the Kb, 1.76 by 10 to the minus 5. So I'm going to set up a Kb ice table. So we have to remember that when we set up a Kb ice table, that hydroxide ion is our formula, is our product. When we set up a Ka ice table, our product is going to be H+. So you got to be a little bit careful there. So ammonia reacts with the liquid water. We're not going to include any terms for the liquid water in our ice table because they're not needed, to form ammonium ion and hydroxide ion. Initially, we've got 4.5 moles per liter ammonia, no ammonium and no hydroxide. It has to go towards the products. It's impossible for it to go towards reactants. It's all 1-to-1, so the ammonia will go down by X and the ammonium and hydroxide will go up by X. That means that when this comes to equilibrium, we'll have 4.5 minus X moles per liter of the ammonia, X moles per liter of the ammonium, and X moles per liter of the hydroxide ion. So this is a fairly small K, right? So I'm going to see whether it's valid to use our small X approximation. And how I quickly do that is I take my initial concentration of my reactant, which was 4.5, and I divide it by my K. And if that number is bigger than 500, then it's appropriate to use the approximation. And it turns out that it is, so it's like, woohoo, we're going to go ahead and do that. So what I'm going to do is I'm going to approximate my 4.5 minus x as just straight up 4.5. So my KB expression is now going to become, it's products over reactants again, x multiplied by x on 4.5, and so that's x squared on 4.5. So all I got to do is equal to KB, multiply both sides by 4.5 and take the square root to get x. So what is x? I have to be a little bit careful. X is equal to my hydroxide ion concentration. So I haven't actually answered the question, right? I have to be aware that I haven't actually answered the question. So what have I got to do here? Well, I can get, if I take the negative log of x, that's going to give me the POH. But I want the pH, right? I want the pH. So I can do that. I can get the negative log of that and get it as my pH. So negative log of 8.9 by 10 to the minus 3. And that gives me a POH of 2.05. And what I have to take advantage of is that the pH equals 14 minus the POH, right? Because the pH and the POH always have to add up to 14. So 14 minus my POH, and that gives me 11.95. And you can see that these two added together give me 14, all right? So that's what I've got to do there. So you do want to be careful with bases because they're often going to ask you about the pH, but what you get from your ICE table is information about hydroxide ions, so you have to do that one little tiny step further. So remember, ammonia is a very, very common base, and then I put this quote from Breaking Bad to remind you, methylamine is an example of an amine class of compound. So whenever you see the word amine, you're often on the lookout for having to do a KB rather than a Ka ICE table. Okay, so